this is a big enough mound I can dig out. And then after a couple of years, I realized it'll last longer if I shovel it all over here by the big pine tree so the sun won't get it. It'll last longer. And since the snow started well over Christmas break, I started a big mound, dug it out. It's the biggest one ever. I could stand up in it, right? The ceiling's this tall, and it's 10 feet across in diameter on the inside. My daughter and I slept in it a couple of weeks, 2 or 3 weekends ago. But yeah, it keeps snowing, so we still have to throw the snow somewhere. I just threw it like 10 more feet further and started a second mound. And so you have to go into the snow cave, and then from there I dug another little hole instead of just making it one big huge thing into a second room. So I started it. Anyway, my wife teaches preschool in our basement, and they love going and playing in it. So anyway, that's how I got excited about the weekend. You guys, yes, Glenn? Yeah, as mentioned on WebAssign announcements, I think I put it there, that's bogus. What the accumulation of your grade is bogus on WebAssign. One, because it doesn't include clickers. It doesn't have anything on the superhero paper stuff yet. It lists your exam score, and it'll list the retake. But I average, so that'll be the score for that. So it doesn't weight them all properly. That's in the syllabus, how you'll be 30% for homework and 10% for clickers and 10% for the superhero, and your finals 20%. That's how you can weight it. But WebAssign, it has the option to weight, but since I want to show you all those things, it doesn't work out. It's not easy. So, yeah, when you're looking at your overall score in WebAssign, don't believe it. It says I have an F. Not necessarily. So, you guys ready for momentum? We're going to pick up a little momentum this class. Thank you. My little lame joke. Momentum's one of those where we use it a lot in layman's terms. And since the retake was now due, and a lot of you are probably more curious about it than the homework, because I can see how many have gone back on homework and actually looked at the answer keys to see my explanations, and I'm always surprised how few, relatively speaking, have actually gone back to even look, and we've already had a test on it. But same thing happens for the exam. Now that the retake was the exact same exam, you can go back and look at its answer key. It has all the correct answers with explanations for you. So those of you that are wondering, oh, that problem was bugging me, you can go look at it now. Yeah, Glenn? If you didn't complete the retake, everybody can still look at it because it has the answers because it's the same exam. Yeah. Again, if you took the exam on exam day, and that's all you did, that's the score you get. If you took it on exam day, you had the option to retake it. And if you chose to retake it, I'll average the scores. And every couple exams, I get one that did not take it on exam day, but since it's available to the whole class, they retook it online. That doesn't count for them because you weren't here. So if you went and did the retake, but you weren't here on exam day, sorry, no credit. But yeah, go look at that because you will need to know this stuff. The final exam is comprehensive. And this stuff will seem like forever ago come the end of the semester, right? Once you have a chance to look at my explanations that are already there, please, so when we meet again, if you have questions about it or it still doesn't make sense, come talk to me or bring it up in class because somebody else probably has the same issue. Because, not on WebAssign, no. When they scan them, I do have all individual responses, but if you can't figure it out from remembering what it's mainly if you can't remember what you answered. But yes, you can contact me. I do have that info. They will send me the actual bubble sheets in campus mail soon too, so I'll have, no, see, there was a dot right here under C, so, in case there's any questions. Okay, so this next section, I should mention, we're going to cover chapters 6 and 7, which is momentum, energy, and then we're going to do chapter 10 on, I forgot what it was called. In my mind, it's projectile motion. What do they call it? Projectile and satellite motion. I'll tell you now, we're not covering all of chapter 10. It's just the part on projectile motion. So the part on satellite motion and orbits, we are not explicitly covering. And I won't ask you questions about, but it's good reading anyway. And 35. Big skip, huh? And that's special relativity, which I think is actually absolutely fascinating. And unless you're getting scared, don't be. We'll have everything we need to know to understand the basics of special relativity. And then it's always fun to talk with your friends. Einstein, well, relativity says. It's kind of fun. But I will warn you, there are some funky things that come out of it that people have a hard time. What? That doesn't make... that's how it works. This is how it defines it. It's a theory of special relativity. And we'll have lay the groundwork for it. And then we'll have another exam on just that stuff before we get too much. So how I like to define momentum. Inertia in motion. It's one of those where, see, I finally come back. Lay people use the term momentum, like, oh, they get a lot of momentum going. And that usually implies to you that it's easy to keep going because you kind of got some momentum built up. And so it'd be hard to stop. Well, that sounds a lot like inertia. Things in motion want to stay in motion. And they will unless you exert a force on them. So like that car on the test question. You go, I forget the values, but if you're going 60 miles an hour, or did I say kilometers an hour, or whatever, and you hit the brakes to slow down, well, there, you just applied a force. So that'll change your motion and cause you to accelerate. In this case, decelerate. You're moving this way, you'll accelerate that way as you hit the brakes. You slow down to 40 kilometers an hour, and then you let off the brakes. Well, ideally, according to Newton's first law, your inertia will keep you going. You'll stay going at that same speed forever, unless a force acts on you. We know in real life a force does act, friction, air resistance. So you would eventually slow down. But if there were none of those forces, you just stay going at 40. So that's inertia. Well, inertia in motion. It makes more sense if I just go ahead and put it. Momentum is usually represented with a lowercase p. And it is mass times velocity. And how they came up with it was they realized, hey, this momentum thing is proportional to mass. We just discussed that, inertia. But it's also proportional to speed, velocity. And it should make sense to you. I gave some presentations, and I can't remember if I already said that in this class or it was in a presentation. Well, I'll just do it again. So forgive me if this is a repeat. Would you guys rather get ran over by a big diesel Mack truck going 30 miles an hour, or little Timmy in his tricycle going the speed of light? What would you rather get plowed into by? Okay, I'm hearing a lot of truck. Why? It's going slower. Momentum's not going as quickly. Yeah, your gut is right, is my point here. Some things in physics they don't settle as well. But momentum is one where you kind of already have the good feel. We're just quantifying it here, defining it. And both of these matter now. Yeah, if you had a Mack truck just sitting still and little Timmy sitting still, it'd be harder to get the Mack truck to move just by pushing it because it has lots of inertia than little Timmy. But if they're in motion, that also contributes. And your gut was right. Even though the Mack truck is huge, it's not going very fast. So its overall momentum is less, would be less than little Timmy, small m. But speed of light, that's fast. That would make his total momentum more than the Mack truck. And you know it'd be harder to stop. Or it'd hurt more if it plowed into you. That's momentum. Okay, I've mentioned before in here that an object doesn't really possess force. That's how I'll say it. I've told you that before. A force is an interaction with something. It doesn't happen until you're interacting with something. But here's one where an object can possess momentum. We can talk about the Mack truck or little Timmy having or possessing momentum. And if they have that momentum, we then try to change it. You know, if you're going to have a change in velocity because of an acceleration, which means there was some net force acting on you, that force causes this change, and so it'll also make your momentum change. And that we call impulse. It's a change in momentum. I'll put it that way. So that can happen two ways. The mass could be changing, or the velocity could be changing. Can you guys think of an example of something moving or something, I don't know, where the mass would change? Bet you can. Yeah, good example. Very good. Your car with the fuel. If the fuel gets used up, then yeah, the mass is decreasing over time. So that technically would change your momentum. A rocket, maybe a more same idea example. What else? Can you think of another one? Well, that's a good one. That's a great one, especially in the winter. Snowball rolling down a hill. Yeah, you get caught up in it. Yeah, it increases its mass as it goes. So as it's going downhill, it's accelerating and increasing its velocity. It's also increasing its mass. So its momentum really picks up, which I guess is one reason it works so well in cartoons. Yeah, good, very good. Impulse is usually written by an I for impulse. And yes, indeed, it equals a change in momentum. And I can't emphasize this enough. A lot of the questions I'm going to keep asking you have to do with that. Impulse is not the same thing as momentum. You're like, duh, I can see that. But think about that as you're going through some of these questions. It always seems to stump people. But it is the exact same thing as a change in momentum. You got to apply an impulse to something to get it to change its momentum. Let's look at this. From Newton's second law, we have that the acceleration is related to the force and the mass. It's directly proportional to the force, inversely proportional to the mass. We've gone over that. We also know that acceleration is the change in velocity with time. So all I'm going to do is put those together. That gives the same acceleration. So if we have the change in velocity over time on that side and the force over mass over there, it's the same thing. It's acceleration. I'm going to rearrange it so that the acceleration goes away, so that the A isn't in this line here. This is equal to that. Can you see the mass and the velocity here? Let's put those together. If you cross multiply, you end up with the force acting over a certain amount of time, these two, equals the mass times the change in velocity. So if you apply a force for a certain amount of time, you get a change in momentum. This is also impulse. That's what we just learned. So this relationship between impulse and momentum starts from Newton's second law. And so you can also think of impulse as, let's just put it here. It's two ways to think of it. It's a change in momentum. But what causes that is a force applied for a certain amount of time. You can't apply a force instantaneously. It takes a certain amount of time, and it'll probably act over a certain amount of distance. And so you can increase the impulse that something feels by either pushing harder or pushing longer. Let's do an example of that. I need 3 volunteers. Anybody fancy themselves as a pitcher? I used to play I think I played baseball more than anything else, and that was my main position. But can anybody throw an egg? Who wants to throw an egg? All right. Come on down. We need 2 people to hold the sheet he's going to aim at. And I haven't had anybody hit anybody yet, so. All right. Thank you very much. All right. We'll have you come over here. And we'll have one of you on that side, one of you on this side, and you'll grab the corners like this. You'll hold that arm up. There we go. All right, we'll move this way so everybody can see. We'll get as far as you feel comfortable going, allowing him to not hit the table. And you become one with the egg here. All right, hold that up nice and high if you can. We'll keep it kind of taut. Yeah, and this is good. That way, if it hits this, we'll see if it lands. So your challenge is to break the egg.
Break the egg?
Yeah. I want you to, when it hits the sheet, you're going to aim for this. Don't hit them, right? You're not going to hit them. You get as close as you want to where you're confident enough you won't hit them. But you throw it as hard as you can. I want you to break it against there. Okay. I'll probably even give you, for an A in the class and $1,000, if you can break it when it hits the sheet. Oh.
I think I cheated.
Try again. Come on. Oh! Swing and a miss.
Sorry about that.
Well, we'll give you one more try. 3rd time's a charm.
Get a little closer, just so I don't miss.
Sure, go get as close as you want. All right, thank you very much. Thank you guys for being brave. All right. This proved my point well. Here, I got some towels, and here's the... And that's what the bucket's for, too. I'll get that. This worked beautifully. Did it get on you?
I think I'm okay.
I got some towels if you need. I've been doing that for maybe, 20 years, and I don't think it's ever broken. When it hits the sheet, it doesn't break. When it hits what? The ground, it breaks. Why? Why the difference?
The blanket, it takes more time.
Time is involved. Very good. Oh, you're so kind. Yeah, just get the big bits and then I'll mop. Yeah, the time is now a factor. It's right here. Basically, look at it this way. The egg's coming in with a lot of momentum. It has mass. It has velocity. and the sheet is trying to stop it. So it's gonna start with momentum mv coming in. And when it hits the sheet, the mv is going to go to 0. So it initially has some momentum, finally it doesn't. So there's a change in momentum caused by the change in velocity, which is that final velocity minus the initial velocity. Or you can think of it as mv initial, minus mv initial. Write it all out for you. Which in this case just comes out to mv because it's going to 0, I guess. My point is the egg is trying to change its momentum. What's causing that change? The force of the sheet acting on the egg for a certain amount of time. The sheet gives, and it extends the time of impact. So if this is larger, the force felt doesn't need to be as big. And it's not enough to break the egg. Does that make sense? When it hits the ground, same exact thing happens. It comes in with the exact same momentum. It has the exact same change in momentum. The exact same impulse is implied. Does that make sense? Whether it hits the sheet or the ground, there's the same impulse applied. The impulse is caused by a force over time. When you hit the ground, it happens quickly. And so it's a small time. So the force felt is bigger, enough to break the egg. Think about that for a moment, and I'll just do one quick little thingy before it starts to smell. And thank you so much. I've never had anybody help clean up so much. Thank you. Got any questions about that? All right, how many of you wear your seatbelts? Everybody's hand isn't up. I'm feeling bad. Airbags. How many of you wear your helmets when you're skiing, snowboarding, bicycling, motorcycling? I sure hope so. That's a cushion. How many of you are high jumpers or pole vaulters? Nobody. Oh, well, the pad. Basically, all that is, you're going to have the same impulse whether you're wearing a helmet or a pad or not, right? You're getting stopped. You're coming in with some momentum, you stop. So you have the same change in momentum, same impulse. But do you want to stop quickly and thus feel lots of force? Or do you want to stop slowly? And even though an airbag, it happens real fast, your helmet doesn't seem to slow you down much. It's enough to increase that time so the force felt goes down. The number one injury with adventure sports and things, cycling and those type of things, is if you hit your head. If you're wearing a helmet, you're way more likely to survive, be less injured. Let's do this one. The basketball, it bounces. Tennis ball. But something fun happens if you bounce them together. It's a collision. We can start colliding things now because these two have momentum. Basically, they fall. The ball hits the ground and starts coming back up while this is still falling. You guys can appreciate this. While it's falling, they're both in free fall. There's actually no force between them because it's like they're falling together, but they're not pushing on each other because they're falling at the same rate, 9.8 meters per second squared. Who's being pulled on more? Is the force of gravity equal? Not everybody has this yet because I saw from the test question. That's why I bring it up. Is the force of gravity the same on these two? Absolutely not. The force of gravity are their weights. And which one weighs more? This one. It's being pulled with more force. Period. What's the same is the acceleration due to gravity. So they fall together. So they don't need to push on each other. So the ball's coming right back up as this comes down and they hit. And what do we know about the force between them? Equal and opposite. Newton's third law. So they're both going to feel the same force, but because this one has a lot more mass, it will accelerate less, and this one a lot more. And you get that shot. This also leads directly right into conservation of momentum. You write that one down. Comes right out of, follows right from that Newton's third law. Let's put that one over here. Conservation of momentum is the other big topic in this chapter. And the way I just remember that is total momentum is always conserved. Some of my physicist colleagues don't like that I say it like this, but it's true. Total momentum is always conserved. Because there's technically these things like, oh, momentum's conserved, well, as long as no external torques and forces are applied, blah, and then you have to, well, it depends on the system you're considering. If you look at everything, then total momentum's always conserved, period. It's just simpler in my mind. So that, like this, the egg coming in. What you would do in this situation is, that means the momentum before, the total momentum before, has to equal the total momentum after. Period. Now, watch this. It can look tedious, but I always write this all out so I never get confused and I don't forget to account for something. So like with the egg and the sheet, you have the mass of the egg with its initial velocity of the egg plus the mass of the sheet plus the initial velocity of the sheet equals the mass of the egg, its final velocity, plus the mass of the sheet times the final velocity of the sheet. I'll give you a moment to write that if you are. So basically it's the momentum of the egg beforehand plus the momentum of the sheet beforehand has to equal the momentum of the egg after plus the momentum of the sheet after. If you do that, then you don't forget anything, and it becomes really simplified. Is the sheet moving initially? So its initial momentum is 0. The afterwards, the egg stops, and the sheet gives just a little bit. It must move. We saw it. That's why it didn't break. So, the momentum of the egg beforehand ends up being transferred to the momentum of the sheet after. So again, you'd have the mass of the egg, its incoming velocity is the mass, in this case, of the egg and the sheet moving together with some final velocity. So the egg comes to stop, but it moves with the sheet. So technically, the egg does have a little momentum. I don't mind correcting this. It's just easier to, when I introduce it, I like doing it this way. It and the sheet combine together and move a little bit. Does that make sense now? We're going to do several of these. Some of the homework problems, some of the test questions. We'll do a lot more collisions Monday. But I wanted to go ahead and show you this procedure so some of you can start working on these on your own. Basically, just consider all the momentum, which is mass times velocity of everything beforehand. Set it equal to everybody's after, and you can solve for anything you ever want to know that they ask for. But it's all because of Newton's third law and conservation of momentum. Let's go back to that basketball. Just giving it time to sink in. So back to the basketball. The force between the two balls is the same. It's Newton's third law. The force on the basketball causes it to accelerate a little, and the force on the tennis ball causes it to accelerate a lot. Well, that force was applied for a certain amount of time. What do we call this? Impulse or change in momentum. They're the same thing. That's going to cause a change in momentum for both of these. We're not changing the mass of the basketball, and we're not changing the mass of the tennis ball, so what did get changed? That's acceleration, which is change in velocity. So this one had a huge change in velocity, and this one had a little change in velocity. So this impulse caused a change in momentum. Notice, though, they both had the exact change in momentum. Change. I emphasize the change again. They both felt the same impulse. This is why total momentum is always conserved. Let's do another one. I found this at a thrift store once. Hopefully you recognize it. It's the thing. Would any of you, again, for an A in the class and $1,000, who wants to hit the brick wall as hard as they can? None of you raised your hand. Okay, why? Tell me why you didn't raise your hand. Because you're thinking I'm stupid, I know. But tell me now, in terms of physics, why do you not want to hit the wall as hard as you can? Because the wall hits back. Good, we know Newton's third law. So the same force I exert on the wall is going to exert on my hand. And add to that. It's going to happen quickly. Just like the tennis ball and the basketball, they're in the same interaction. So it's the same amount of time for both. That's why that can work. And hitting the wall is a short time. So yeah, you'll be a big force. Let's draw that one. For those of you that haven't quite seen it yet or like visuals. So if you have the same basically, you can have big force for little time, or you can have little force over relatively big time. Still the same impulse, but yeah, you guys are smart. Thanks for not taking me up on it, because I always worry somebody will want to. They're going to break all the bones in their hand just to get an A in physics, and it's not worth it. But if you're wearing this, how many would do it? More of you trust physics now. The rest of you aren't quite convinced. Come on. That's why I really bought it. Yeah, you can hit it as hard as you want. Because of the cushion. It doesn't seem like much, but that's enough time that now the force felt doesn't hurt my hand. Here's my favorite way to emphasize this time of impact. Because things happen quickly when things collide, so it's not always easy to see. Let's see. All right, I take this ball. It's squishy, and it's going to come in with. I'm going to give it some momentum, and the board's going to change its momentum by applying an impulse to it to stop it. And what I want you to see is it spreads out. So, high-speed camera. Maybe some of you can do that. Does the iPhone 6 have nice slow-mo or something? But you could see it spread out. But even though we couldn't witness it during the impact, you can tell it must have taken time to spread out and come back. And that whole time it was in impact. And there was forces applying. The force, in this case, I'll ask you. What was this guy's change in momentum? It came in with momentum mv. We don't know what it was, but it's mv. It has mass, it had a speed, velocity. Then what happened? It stopped. So there was a change in momentum of so it came in with mv and went to 0. So the change in momentum was that amount. Then what happened? It bounced back. So it regained momentum? Yeah, the wall is pushing back with equal force. That force made it stop, but it's still in contact. It's spread out. The wall's still pushing and accelerated it back. So it made this change, but it also did what? It went from 0 to, yeah, we'll idealize for now, and it pushed it back, bounced back. We'll say ideally it came back at the same. So there was another change in momentum of mv. So what was its total change in momentum? Ideally, it is equivalent. So it comes in with mv, comes out with mv. So what was its total change in momentum? I heard 0, I heard mv squared, 2mv, we got 3 answers. Okay. Clue. What's different? Oh, yes. Bless you. That was going to be my clue. Velocity is a vector. He says it changes direction. So, let's say, here, I'm going to draw a wall. And the ball comes in. If we say that's mv, and it's a vector, so it's to the right, well, let's make that positive. It's going to go to 0. Still 0, but it's going to come back out. And if we're saying it has mv, but now what? Negative. It does change direction. So it ideally has the same magnitude of momentum in and out, but the direction changes. Momentum is a vector because it involves velocity. And velocity is a vector. So when you figure out the change in momentum, you take the final momentum minus the initial momentum. The final is negative mv minus the initial, which is positive mv. And what do you get? You guys still with me? So the negative is the final. The positive was the initial. What's a negative mv minus mv? Don't you just love adding negatives? Negative 2mv. So whoever said 2mv was the closest. But yeah, it's negative. It had a change in negative. Now think of that conceptually. It came in with positive mv. The change was directed in the opposite direction. It caused this to stop and regain going back the other way in that direction, which is opposite. So yeah, ideally, when something bounces, it feels twice the change in momentum. which is twice the impulse. Because that force was applied to stop it and to let it bounce, assuming it bounces. Not everything bounces. Now, when we get to chapter 7, we'll discuss a little better with energy. Non-ideally, some of the energy is transferred to the board, or sound, or to deform this. And so some of that energy is transferred elsewhere. It also takes some of the momentum. And so it comes out with a little less than it came in with. But we'll worry about that later. But what's fun is, what if I throw it faster? What do you expect to see? A bigger splat? Why? Yeah, it's coming in with more momentum. So it'll take an even larger impulse to stop it, change in momentum. And one way to do that is to extend the time, which will give it time to spread out more. And sure enough. Bigger bounce too. Because it was feeling a bigger force to stop it, but it also felt a bigger force pushing it back out. Much bigger. Can you guys see that okay in the back? So here was initial. Here was that second one that came in with more momentum. Besides, it's always fun when you can throw a ball at the board. Yeah. Yeah. So it went here, and it spread out enough to influence the chalk dust there. So a portion of this, yes. My guess is it was in greater contact here. It's darker. It took off more of the chalk there. That was in contact for a longer amount of time. And maybe you saw the board wiggle. Some momentum is transferred to the board. It's not like the brick wall. And it could have been here, and then the board gave a little bit. So it wasn't pushing as hard there, maybe. Good observation. Anybody want to try it this way? Since we have the egg and mop out. Let me do this way first. What should happen now? Yeah, boring. Same thing happens, but the tennis ball runs into the ground, and so it's anticlimactic. This time, don't watch the tennis ball. Watch the basketball. It bounces about there. There. Let's do it with the tennis ball. Watch the basketball this time. Notice it doesn't bounce up as high? So it's transferring some of its momentum to the tennis ball through that impulse. You can also think of it as it's transferring some of its energy to the ball, tennis ball. So, what do you think will happen? I got a mop, so I don't care. You think it'll bounce? Why? I think most people think this is going to break as soon as they collide. It's going to drop, and as soon as the basketball hits and starts coming back up, so there's some cushion to this. This gives some, huh? Okay, any other thoughts? Okay, well, if it's not going to break on the basketball, what's going to happen? It's going to go up. Then what? What's it going to land on? Maybe we should try to catch it. Okay, front row, at least be paying attention here. Ready? At least these aren't fresh eggs, so it's not quite as messy. All right. So yeah, you were absolutely right. The ball gave a little, kind of like that. Extended the time of impact, so the force needed was less. The force the basketball felt was less, and the force the egg felt was thus less. Try saying that fast 3 times. But again, as soon as it hit something hard, it stopped all at once, and it died. Let's see. Oh my gosh. All right. I'll do one more. We got 5 minutes. Oh, did you guys realize there's no homework due this Sunday? You had a test. We just started chapter 6. We haven't finished it, so there's nothing to. It's not due yet, so you can still work on it. It's available, but there will be another pre-lecture. I'll do more on momentum, and it should be available as soon as class is over. Let's do this one, and then end. Some of you might have seen these. They're called happy sad balls. Some people bounce, no bounce for the other companies that sells them. They look the same. They're the same size. They're both made out of rubber. One bounces, and one doesn't. So people refer to this one as the happy ball, whee, and this one the sad ball. Same mass, whatnot. I'm going to roll each one down the incline, and they're going to hit this block. They could fall over. Will they knock them down? Will they both knock them down? Will one knock it down and the other not? And if so, which is which? I'll get you thinking. This is how you should reason through these. Okay, they have mass, but they're about the same mass, so that doesn't matter. They both start at the same height. So how do their velocities compare right before they hit the block? Should be the same. Well, if they have the same mass and they have the same velocity, right before the collision, the interaction, they come in with the same momentum. Glenn? Okay. I'll sum that up with, this one bounces. So there's a difference. And you think that'll, long story short, mean they'll interact with greater force compared to this one? Any other thoughts? What's that? The first thing you said? This one has less give? So you think it'll knock it over? That makes sense, yes. Rubber sledgehammer versus non. Yeah, the rubber's not going to provide as much effect because it gives, thus there's less force in the interaction. So that would mean towards this. Oh, we have two very logical for both. This is where I'm always tempted. Should I let you dwell on it and suffer over the weekend and we do it Monday, or just do it now? Yes? The karate chop does explain how this works. Yeah, just with the karate chop, whether you bounce or stop matters. Let's do it. All right, here's the sad ball. We'll start with it. Oh! Could have been a fluke. Let's try it again. Oh! All right, happy ball. Could have been a fluke. This is how I want you to remember it. The ball that bounces feels twice the change in momentum. The sad ball, its change is just mv to 0. The happy ball is mv in, mv back in the opposite direction. So it feels ideally twice the change in momentum, which is twice the impulse. To provide that impulse, there's more force involved in the collision. So, life lesson. Next time someone pushes you out of an airplane and your parachute doesn't open, because that happens all the time. Do you want to hit the ground and bounce or go splat? I hope you want to go splat. Relax. Enjoy the ride. You'll probably still die anyway. But maybe you just break every bone in your body, but you're still alive. Because if you go splat and you don't bounce, you don't feel as much force. Because there's less change in momentum, less impulse on you than if you bounce. See? So really, this is the happy ball. This is the sad ball. And last thing, honestly, drunk drivers. Who usually gets injured in a drunk driving collision? Not the drunk person. Why? Quite often because they're so out of it and relaxed. They kind of go splat more. It's those that tense up, and they essentially kind of bounce. It's like hitting a brick wall now instead of giving a little. So think about that. Have a great weekend.